Today's top supercomputers have hundreds of thousands of nodes and sophisticated low-diameter interconnects between these nodes. These powerful machines can help us solve complex problems in science and engineering. However, fully utilizing their computational throughput requires effective parallelization of the application software that executes on these supercomputers. Particularly important is avoiding bottlenecks in the interconnect that links the processors. Load imbalances and unnecessarily long communication routes can negatively affect application performance. For example, both green and orange communication streams are routed through the link between nodes 5 and 6. This creates a communication bottleneck on this link, which may reduce application performance. Profiling tools are often used to analyze communication patterns and identify bottlenecks in supercomputers. However, these tools produce gigabytes of output data on large-scale machines. Analyzing their output to identify bottlenecks is a humongous challenge in itself. Our work designs a visual analytics system for understanding and addressing communication bottlenecks in large-scale supercomputers. Our visualization helps application developers comprehend communication patterns between several thousands of compute nodes in the presence of complex interconnects such as the 5D torus and dragonfly. Our system also suggests new routes between compute nodes and new mappings of processes to nodes that address bottlenecks in the communication interconnect. Our system consists of 3 views. The first of these is the communication view. It shows an overview of the communication as a node link diagram. Routes between source and destination nodes are visualized as stacked lines, which indicate the total message size transferred between these nodes. The second view on the left is the metric rank view, which shows ranks and values of metrics related to communication bottlenecks. This is used to filter values so that the users can explore the desired aspects of their data. The detailed route view at the extreme right provides in-depth information about selected routes in the other views. Communication route is drawn as a continuous line with horizontal and vertical lines passing through the diagonal squares corresponding to the nodes and the gray squares corresponding to their neighbors. This view also provides rerouting and remapping suggestions. The system shows suggested rerouting with a purple line. The user can also see the communications after applying the suggested rerouting. The system provides several scalable visualization methods, such as aggregation for the communication view and the detailed route view to show communications between more than thousands of nodes. The system allows the user to interactively apply these methods. Please refer to our paper for further details about the visualization design, interactions, and algorithms supported in the system. We demonstrate the utility of the tool with one representative case study, which is an analysis of communications between 2,048 nodes. We start by examining an overview in the communication view. We apply node aggregation to the communication graph. We notice that there are several distinct clusters of nodes with little cross-communication between them. This indicates that many communications occur only between disjoint subsets of the application nodes. This can be seen very well in the communications at the top right, where 2 of the aggregate nodes have internal communications within the aggregated compute nodes, with large message sizes indicated by the dark blue self-loop. We select this cluster with the lasso to review these communications in more detail without aggregation. However, there are still too many routes displayed to clearly see where the bottlenecks are. From the metric rank view, we select the communications that have the top 5% highest loads. Now we see that many of these communications have long lengths and large message sizes. These communications are likely to reduce communication performance. Additionally, these communications occur within 3 specific physical locations, as shown in the detailed route view. To see the routes in each area in detail, we apply folding of unrelated regions. From this, we can also see that most of the communications are isolated to specific locations. This indicates that many links near these locations are not well utilized. Thus, there is a high possibility that we can find improved routes to better balance the load across the available links and improve performance. We then query the system for rerouting suggestions for these multiple routes. We can see that the suggested routing better utilizes the available links. In addition, the system also shows that this routing reduces 88 megabytes from the highest load on the links in total. Thanks for watching.